All right, so a rehash from last class, we went over the definition of the analysis of variance. We went over the chapter problem, which I don't know, I'm a little old school and old. So again, it was kind of interesting. I think it kind of made sense looking at it. The data we walked through, look at some of the descriptive data, and talked about the need of how what we're doing, which is true for every chapter, is we can't look at anecdotal, what they call it, informal or subjective comparisons to make these inferences. What we need to do is need to do the statistics, and that's why we're doing the analysis of variance right now. We kind of had this little three-step interactive thing where we were just asking you guys to develop the hypothesis, and we had some participation on that. The next thing was for us to think about and identify what the one factor was. And then I believe we read this little paragraph right here that communicated to people where the name factor comes from. Because if you look at the research that really teaches, the appropriate word is factor, even though we use the word independent variable very commonly in psychology. And that's because we're always interested in independent variables. And then also factor is appropriate, as well as factor, levels, no factor, independent variable. Actually, I don't know the other one. Let me see. Treatment. Treatment is the last one. Factor, treatment, independent variable, right? So those. Then we talked about how the F distribution works, and essentially what the F distribution is, it's a ratio. This ratio is designed to compare the variance between samples to the variance within samples. Now, variance between samples, again, we got to think about, we got 3 samples, right? So we're going to compare the variance between those. So we're looking at how those 3 samples differ, right? And then when I sit back and use another phrase that says the variance within the samples, then we're looking inside those samples and trying to see what the variability looks like there. And essentially, if our effect works, if Dr. Barnes is saying he's teaching online classes and he believes that online classes are better, right? Then there should be more variance between the samples, right? That means if I look at the class that has online, the class that's hybrid, and then the class that's face-to-face, right? Those scores should not be the same. Between those three samples, there should be a lot of variance or variability between those samples, right? But if I'm doing a good thing, the variance within those samples shouldn't be so great. Now, what that means is this: everybody, if this right here is the online virtual instruction environment that we're doing, right? That means everybody in here, and when I look in this class, all y'all should be pretty much similar. When I go look at the face-to-face classes that I've taught in the past, when I look at the people who were enrolled in those courses in the past, right? It should look similar. And the other condition was what, like a hybrid math class, like some here day, not there day. When I look at those people, whatever score they are, they should actually be similar. So you have to conceptually think about what we're talking about. We're talking about between samples, comparing the 3 conditions. And then we're also talking about the denominator, how much variability exists within each sample. And that's kind of the situation that we always get. But, you know, there's variability all the time, everywhere, no matter what we do. All right. All right. So I like that. That makes me stop looking at the camera altogether. So that's what the F ratio is all about. Then I think we went into detail about how the F ratio changes depending on our sample size and depending on our categories. This right here is assuming we have 4 categories, and then we follow by increasing the size of the sample. Start with a very small sample, then we went up to larger, becoming more reasonable. But then when we get to this point, it's not changing that much, right? It's not, when you get here in 19, 29, and 59, it's not changing that much. However, it does change. And that's the reason why we always got to go to the back of the book and we have to use that table. Because when we go to the back of the book and use that table, we're able to find out, all right, that value of 0.5, right? A value of 5 or 1, I just realized that. This is a deceiving graph. It does still change though. But this graph is deceiving. And this goes back to what we talked about chapter 1 at the very, very beginning. The reason why this graph is deceiving is because, again, if I look at all the other graphs, I'm going to go back. Yeah, the axis changed. This only goes up to 4, 4. I don't like that. Although it is different. Even though the graphs are not used for this purpose, it is different. If you sit back and look at the very first graph, it goes from 0 to 4, which is probably right here. So it's plotting the entire distribution of the graph on that. Whereas yeah, funny. Right. So the other graphs a little bit later are going all the way up to just values of 4. So this is a deceiving graph, but I think it does show, and it is true, that the shape of the distribution does change. So that's the reason why we always got to go to the back of the book, because the an F value that we get, depending on the distribution, it may or may not allow us to reject the null hypothesis. So you have to look at that. Kind of got off topic, guys. I'm sorry. The phone distracted me, as well as realizing that this graph is kind of deceiving. I'll see what I can do to fix that in the future, because I love where I got these graphs. But it does change. All right. Then we went and talked about the back of the book. We've been doing this for so long. It's the end of the semester, but this is what those typical charts look like. And what we did with here is we're following the 2 degrees of freedom. So I showed how if we were actually trying to find a critical value, the value that we need to surpass in order to reject the null hypothesis, those 2 degrees of freedom would allow us to do so. So again, the first one was like, what, 3 and 3? That would be our critical value. That means if we do an ANOVA with the sample size and design consistent with those degrees of freedom, we must have a F value greater than 15.439 to reject the null. If it's 3 and 9 degrees of freedom, greater than 5.1, I'll round up a little bit. We go down to 3.9 when we get to 3 and 19, and then we get a little bit more reasonable, doable as a result of increasing our sample size. And that's why it's so important to do that, to make sure that you have the appropriate sample size in this so I can see myself. The sample size, when doing that, the greater your sample size, the greater ability for you to reject the null hypothesis. I mean, that's always key. That is the intermission where we were. I do want to ask if anybody has any questions before I move forward, because I'm ready to go, ready to move. I want to make sure that you guys have any questions. If you have any questions, we can talk about them. All right. Now, looking at this right here, the F value. I think we read this already, but I'm going to go over it again. And I'm going to go over the part that's going to be relevant to our discussion. The numerator of the F test statistic, the numerator measures variation between samples, right? We look at each of the samples, the sample means, right? How do they differ? The denominator depends only on the sample variances within, right? Depends only on the sample variances. That's looking at how much variability is occurring in each of those samples. And it's not affected by differences among the sample means. The first one is, but the second one is not, right? I hope that makes sense for you guys. If you don't understand it, please let me know, right? Next, sample means that are close in value to each other result in a small F statistic. So let me show you what this means. I'm going to try to draw this. Now I'm doing this impromptu, so forgive me. All right, so we got 3 samples, right? Remember that little stem leaf plot we had before? So we got 3 samples that look like this. Okay, the numerator is looking at the variation between sample means, right? So plot, sample mean is always right there, smack in the middle. I should have made this a different color, and I will undo. Sample mean is always in the middle of a box plot, right? So these lines right here are the sample means. So when I look at the numerator of this F value, this right here, I am comparing this mean to that mean and this mean, right? The variation between those samples. That's not a big difference, right? So as a result, we're going to assume this. Let's assume that the denominator is 1, which means we got a little bit of variation in the sample. We're going to hold this constant, though. I don't want to really get into this discussion right now. I just want to show you how all things held equal, which means the variation that we get in the sample, right? Because when I do my other example over here, I'm going to make the same assumption that my variation within the sample variances are the same. So we're going to keep this green right here. So these right here are going to be the same. Now, looking at this right here, these, the numerator of the F value is said F has a numerator and a denominator. Right here, F has a numerator and denominator, right? So what I'm saying here in this sample is that sample means that are close in value to each other result in a small F statistic, right? So these are pretty close to each other. So I'm going to give that a value of maybe 2.4 because they're kind of close together. Now, it's not as simple as me making up a number, but again, these are close to each other, and the variance between samples is not that great, right? We sit back and look at the number line. We got a 0 right here. We got a 1 right here, a 2, and then 3, right? So that's the number line where it's going. And the variability that we have is kind of around here, but then you got to factor in these endpoints right there. So we got variability between the sample means as being reflected by a value that is approximately 2.4. Right? Now let me look at another possibility. We're going to do this a different way visually as well. We're going to do another number line, right? And it's going to start with 0 as well. 1, 2, 3, 4, 5, 6. Same thing. I'm actually going to have the first one up top. Well, it's going to draw the same, but it's not across the same number, right? Then we got a group that's way out here. I was ready to cuss, but I'm not going to do that, right? Way out here. And then we got another one that's here. Now, again, the mean, according to box plots, are right dab smack in the middle. Right? 3 samples, 2 possibilities of an experiment. We ran the experiment year 1, and this is how close the data is. This is before the pandemic, right? We looked at online courses, the difference, et cetera, and this is what happened. Now, the pandemic occurred, and we're looking at the same 3 classes, face-to-face, online, and hybrid. Now, because of the pandemic, these means are very different. So since these means are very different, let me see if I can kind of internalize the range. We got a range right here. This is where the last one stops. It goes all the way over here to 6, right? It's not going to be any value of 6, but I'm going to say that range is somewhere around, I'll say 4.5. 4.5, right? Now, before, we're just going to ignore the new denominator because we're just saying that those things are kind of just held constant with this example, right? When you divide 2.4 divided by 1, you get a value of 2.4. That's kind of a small F value. Now, these differences over here are greater, right? So as a result, the F value is greater, and the numerator is greater. So we'll take a 4.5 here divided by the same thing that's happening within that. So as you can see, since these means over here have a greater difference from each other, right? We have a greater F value. And that's exactly what this sentence is saying. And the reason why I went into this conversation, right? It's saying small sample means that are close in value, right? Like these, result in a small F statistic. That's small. Small is relative, right? Forget about the large p-value, right? So we conclude there's no significant difference, blah, blah, blah. Let's go on to what the next one says. The next one goes in to say that sample means that are very far apart in value result in large F statistic. So this isn't very far apart because I'm working on what I just in class, but you can imagine this number is larger than that. Ooh, the more apart we go, the larger that number will be, right? So sample means that are far apart, right? All denominators held equal will result in a larger F statistic and a small p-value. Let's forget about that. That's just what we means. We're going to reject the null. So we reject the null, or AKA the claim. That's just me trying to sit back and show you visually. There's another way I'm going to show you how these things occur as well. And this will be a little bit of support with some math on it. This graph, I actually don't want to go into anymore. This is really just showing a couple things. One, that the distribution is all values have to be positive. The distribution is skewed, and how you can sit back and reject the null. You reject the null if it's in this region, and you fail to reject the null. No, you fail to reject the null if it's in this region, right? If the F's in here, it didn't reach that critical period. But then you reject the null if it actually is in that critical region. And we always got to sketch, label, and shade to see that. That's all I want to say with that. Now, this table is a very powerful table that I think is another way of showing us how the F values and having means that are close together will result in small F value, and means that are far apart will result in large F value, but it's done by numbers. Now this table, let me tell you, this is one other thing. I think this table took me, I might've saw this table 3 years in a row and didn't quite get it. And I wanna make sure that you guys get it, because I think this is what's really important for ANOVA, to make sure that we understand this kind of stuff. Now, what I'm gonna tell you in a nutshell what this is doing. What we're doing here on this table is essentially, we got two sets of data. We got data set A and we have data set B. Now I'm going to ask somebody, look at this. You guys serious? What in the world is different between data set A and data set B? And I'm going to cover up all information that is irrelevant to the discussion, so it's not distracting you. Again, I'll repeat the question. I know y'all might have been.
Is it that is X1 is 5.5 and then B is 15.5?
Yep. Now that's a good point, right? Now you pointed us exactly where we need to be looking. So now I need some other people to show me, to go in a little bit more detail. How specifically are they different, right? Because now we're focusing on exactly what you mentioned. Draw. These values are different from these values. How are they different?
It's added 10 to the other sample.
It's adding 10 to the other sample, which is the sample that we have over here. So, and again, it's so funny. It only added to one sample. It didn't add to all of them. We're going to pretty much do the same process with 3 samples, and we're only changing. I wish I could get I'm not sure if y'all hear that, but my email's dinging and chiming. But again, we only changed one sample. Absolutely right. Okay, so we have that information, right? Now, what, you know what, guys, give me 1 second. I'm going to pause the recording. We're recording again now, guys. I'm really sorry. I actually forgot the point that I was talking about here. But yeah, what does N mean? We look on this slide. What does N mean? You guys remember? These are the kind of things that are so crucial that can make it so some people know and other people are like, I don't know what we're doing in class, Dr. Barnes. What's N? Scary because I still don't have an answer.
Sample size.
Sample size. Yep, sample size. All right, it's excellent, right? So what does X bar stand for? Somebody else share some love a little bit. You got more than a few voices.
The mean.
All right, the mean. Now I'm gonna go a little bit deeper and say sample mean.
Okay.
Right, but again, you're right. That's just me being obnoxious. Okay. Ooh. What does S squared mean? Now this is taking it back.
Variance.
Oh my goodness, it ain't taking it back too far because you know what it is. S squared is the variance. Now, this is just a question I'm just going to ask you just to see if y'all remember. What is S?
Standard deviation.
Oh my God, you know what? You're making me cry. I feel like I am teaching somebody something in this class, right? All right, exactly. S by itself is standard deviation. S squared is the variance. Absolutely right. Now, so we have all that information for all three of our samples, right? We have the sample size, we have the mean, and then we have the standard deviation. Now, let's bring our attention to how these samples differ. How do the standard deviations differ between these two? I think I said standard deviation, but how do the means differ? Again, I think we're talking on the other side of our cameras and we're still muted.
They're 10 apart as well.
They're 10 apart as well. And let me ask y'all this. How does the sample size differ? These are easy questions for us to answer.
It doesn't differ. They're both 4.
Doesn't differ. They're both 4. And look at this, the variance. The variance is looking at how these scores vary within each other. This is what the denominator of the F value is looking at, the variability within a particular sample. We changed those scores, but it did not change at all. The variance within sample 1 is still 3. The variance within sample 1 for data set B is still 3. And that's because how those scores differed from each other, AKA the variance, it didn't change. Didn't change at all. Okay, now let's get into understanding this a little bit more. Okay, and let's only look at half of this, right? So sample means we look at the F value. You can't forget about what we need to do to get F, right? I want to make sure we all are aware that F is calculated by looking at the variance between samples and then also looking at the variance within samples. So we're going to be looking at both of those today, and that's what F is. I'll make that like orange. Okay. Looking at the information that we have. Step 1, we got to get the variance between samples. Now, many people always ask, like, where in the world does this come from? And for a while, it took me a while to understand where this came from. But I am going to show you, right? Now, I should have a bar here to cover this up because this should be X bar. It should be X bar, X bar, X bar. X bar sub 1 equals 5.5. This 5.5 is the same exact value that we have there. This X bar sub 2 equals 6, same value that we have here. The next X bar, same value that we have there. Now, what they did is essentially this. We're talking about the variance between the samples. They essentially calculated the variance between the sample means, right? Variance between sample mean. That's actually what I did. I wrote up here earlier in the slides to help us. They call it variance between samples, but I think what would really help all of us is say variance between sample means, or variance variance of the sample means, right? That slight terminology would make us be like, oh, I know what you're talking about. But we sit back and had these fancy words and everybody's like, I don't know what they were talking about. So we took these means, we treated them like scores, and we calculated the standard deviation. If anybody wants to prove me wrong, when you do the standard deviation, I promise you, you get this value right here. When we square these, the standard deviation that we get, we're going to get this value right here. And look at this value. This value is that mystery value that we were just saying right here, that many people can't follow this chart because we don't know where that 0.083333 comes from. Now, if you read the textbook, it goes into detail and it does explain it, right? But it's not the best. It's, like I said, there's a kind of a stat nerd running the course. Now, to calculate the full variance between samples, it's not just getting the variance of the sample means. We also got to factor in sample size. So let me clear this. So we bring together sample size is important. So we have like 4 times, right? 4 times the variance. And that gives us a numerator. When we're doing the variance between samples, the numerator is going to be 0.3332. And we got it right there. Now, the next thing we need to look at is going to be the variance within sample, variance within sample. To do that, we're going to look at this first value. This 3 comes from essentially getting the variance. It comes from taking the variance of that sample and also taking the variance of that. And what does it do? If y'all look at the math, what does it do with those 3 variances?
Add them together.
It adds them together. Step 1, she's not wrong. I love Siani. All right. What else do they do after they get those variances? Somebody else.
Divide the sum by 3.
Divide the sum by 3. Okay. Now, I love that you said that because it might not be apparent. Divide the sum by 3. How many scores are there? 1, 2, 3. So it's not just as simple as dividing it by 3. It's actually calculating the average. That's how you get the average. You know, if you have 4 scores, that would have been the number 4 here. If it was 5 scores, that would be the number 5 here. So it's not just dividing it by 3 and we think that we would always divide it by 3. No, they're getting these variances and they're calculating the average variance. The average variance. And that will give us the value that we have right here, which is the denominator, which is the value that we have right here. So this is our F statistic that we have right here, F. We'll divide the between sample variance and the variance within samples. Those are the scores that we have right here. We got an F value of 0.1428. 0.1428. That's small. But consistent with what I drew on the last page, yes, it's small, right? But the sample means are also close together. I'm not going to do my horrible artwork like I did last time, but the sample means are close together. Look at this, 5.5, 6, and 6. That ain't nothing to sing home about. I'm gonna be like, hey mom, I did something 3 times. That's like taking them out of stats class. Yeah, y'all know stats. You can't, usually the math exams, you can take 3 exams. You can take it 3 times, right? I don't think anybody's going to reach home to their mother when they be like, what'd you get the first time? A 5.5 out of 10. Okay. What about the second time? 6.0, 6.0. Like, oh, you did the same thing all 3 times. Like, you're not going to be happy. You're not going to tell your mom. You just, it is what it is, right? Now, let's sit back and use that same analogy if we're going to assume that these scores are like what you got on the math exam. I already did that already, right? Let's go to the other side, sample B. Now imagine this is your test score, right? You took the math exam 3 times. First time you got a 6. We're going to go the other way around just to make it so you can have a reason to call your mother. 6 out of 10. Then you got a 6 out of 10. And then you did so well, and plus you did the extra credit, that you ended up getting a 15.5 out of 10. Now, this difference, right? This score is so different. That's worth calling home. That's worth telling your mother. That's worth getting excited about. So that phone call to your mother might actually be justified for this if these were test scores, you know, per se. All right. But let's do the same exact thing that we did the last time. We're going to do step 1, variance between sample means. I added that, variance between sample means, right? So we're going to get these 3 means. We calculate the variance, and when we calculate the variance, we're going to get this value right here. And then we calculate the variance by squaring the standard deviation. And then, of course, we find that value. And like I said, even though the variance between sample means it's not just completely calculating the variance, we also got to take in sample size or factor in sample size. That's why we'll multiply it by 4 right there. 4 times our variance, because it's a whopping value of 120 point blah, blah, blah. So again, look at how sensitive the numerator is. All we did is change these values by 10, right? But when you look at how different the numerator is, oh my goodness, it's actually improved by, I think, more than 100 points, right? That variance between sample means was greatly influenced. Now, the same math from what we did before can be done again. All right, let's move on to step 2, which is the same thing that we did the last time, although I didn't walk you guys through it. This is looking at the sample variance. 3.0. We got our 2.0. And then we got our other 2.0. And just like I said before, we're not dividing this by 3, and we would always ever divide it by 3. We're essentially calculating the mean. And the mean of those values gives us a value of 2.333, which will match exactly what we have right here. It's a different way of doing it. Now, like we said before, actually it's not on the screen anymore, but in order to get the F value, we'll take this value and divide it by this value. And that will give us our F. And in this situation, look how drastic. We got an F of 51.5721. That's crazy. And just like we said, a large F value and a small P value. The likelihood of getting this, if all 3 of these samples right here, sample 1, sample 2, and sample 3 were equal, man, that's unlikely. There's no way in hell you'd get that. That's like a 0.0000118 point chance of getting an F value this high if all 3 of these samples were equal. So what do? We reject the idea, we reject the claim, we reject the hypothesis that all 3 of these are equal. And we're just like, it must be something there. We reject the null hypothesis because we think that these means are actually different. There's no way they can be equal. The likelihood of that happening is 0.0000118. Trust me, there isn't nothing I would do to bet money on with those kind of odds. If you bet on something thinking that you're going to win with those kind of odds, you might as well look at whatever you're betting as a donation to charity. You probably not getting that money back. All right, let me see. Okay, now we went through a lot, right? I'm going to, before I move on to the next slide, I want to make sure that you guys are okay and comfortable with what we've talked about, because it's a deep kind of discussion. Is there anybody who would like me to make sure I reiterate any aspect of this chart, AKA this discussion, to make sure that you understand and follow the important point that I'm trying to make with this graph? And you know what? I'm gonna ask y'all this. Y'all put it in chat as a direct message. I don't want you to have to open the mic and then sit back and say your point, and then everybody knows it's you and you're embarrassed. No. This class is for all of you. So if you have an issue that you're worried about, I'll give you some time, because it probably takes a little time to type it into the chat. But please let me know what part or what question you're confused about so we can reiterate it. And if you don't have anything, do me a favor and send a direct message to me. Nobody else needs to see it, and write none. So I will be waiting for, how many people in this class? 7 nuns. Okay, good question. Okay, none. Somebody sent none and spelled it like a nun. I hope that's a joke. Yeah, I think it is. All right, so I got 4 responses. That means I need some more. I'll show you how to do this, son. Okay, step 1 we'll go over. All right, so I got 2 questions here. I got a question about going over step 1, right? And then also I have a question about knowing what S squared is, right? So I'm gonna try to do both of those to make sure we get this point, because again, I'm not in a habit or business of teaching and people not understand. That's not why I'm here. Okay, so let's go with S squared. S squared stands for the variance, right? Now this goes back to chapter 3. Where we first talked about measures of variation, right? S squared. Now I can't do it in the text that we have, but that's what S squared is. S squared stands for variance, right? And we talked about it in chapter 3, where we first talked about measures of variation. That's what variance is. It's a measure of how much these values and scores vary within the sample. So I'm going to say, for example, right here, annotate, work out. We're looking at these scores right here, and the variance is essentially saying, all right, how much do these scores differ amongst each other? We got a 6, we got a 6, we got a 7. If we didn't have this 3 right here, there wouldn't be that much variability, right? But we do, right? So that kind of makes the number kind of just change a little bit. That makes it a little bit more variability, right? Let's look at one of these samples that doesn't have that much variability. Looking at the variability, actually all of these has variability, so I'm gonna change the point a little bit. Let's look at the variance here. Essentially what we will be looking at is saying, all right, we're looking at these scores, the 6 and the 5, the 5 and the 8, how much variability exists between those scores, right? The 5s and the 6s, that would be happy camping, but then we mess things up by going all the way up to 8, which isn't that bad, right? But the thing is, the 5 is the lowest score, and it's weighting it down to the middle a little bit more. Let's look at conceptually the variance of this sample. Same thing, right? We're looking at the variability within a sample. Right here, we got 2 7s, right? A 6. Again, without that 1 4, like it wouldn't be that bad. But that 4 drags us down a lot. It does. It drags us down a lot, right? So that's conceptually what S squared is and the variance. We are looking, and that's why they talk about the variance within samples. We are essentially looking within that sample and asking the question of how those scores differ. Great question, great question. I hope that helped. Let me see, let me clear all this. Okay, the other question we had was, let's do step one again. So let's do step one again, all right? Step one is the variance between samples. All right, I got a chat. Okay, perfect, thank you, thank you. All right, step one, we got variance between samples, right? So I mentioned before, I wish, and again, I'm not a mathematician, trust me, I don't set these things up, so no one's really gonna listen to me, right? But we call this variance, let me see, variance between samples. But I actually think the better name to help us understand would be variance between sample means. Because if you say variance between sample means, then I think people can understand what it is that we're doing, right? We are essentially looking at the variance between sample means, right? So, okay, what does that mean? We will take the sample mean, which is this. We will take the sample mean, which is that. We will take the sample mean, which is that. Now, I wish they were written how we went up above right here, because it would be like perfect to kind of show you how they're similar. But essentially, what we're doing is we're going to look at these scores right here, and we're going to say to ourselves, just like we said with the three examples up here, how different are these sample means from each other? We got a 6.0, we got a 6.0, and we got a 5.5. It's not a lot, right? That's not a big variance at all. That's conceptually what we're looking at for this. Now, let's look at how it changes when we do it across the others, because now when we added 10 to each, right, over here, now let's look at, it changes everything. Now we're looking at the variance between these. We got 2 6s. If we ignore this, 2 6 at the bottom will be perfect. They're like twins, identical twins. But then we got a 15.5. You know how far apart 6 is? If you got $6 and broke, you know how hard it is to get $15.5, right? Actually, I don't want nothing in the chat. Don't tell me how y'all get your money. But you think about that. You broke and got $6, but you want something to eat that costs 15.5. You ain't eating, or you're not eating that. You got to change your menu, your meal. So there's a lot of variability within this sample. So the variance between these sample means is much greater than the variance between these sample means. And that's what step one is looking at. How do we do it? I will go through and refer back to these numbers, right? We'll go through the slides. We're going to do the first one. It's not moving. We're going to take the 5.5, the 6.0 to 6.0, and we're going to calculate the variance of them. And what I ended up doing, I took 2 steps. I probably should have just got rid of the standard deviation. But I calculated the variance of these scores. And that gave us the 0.8333, 0.08333. And that 0.8, wow, I keep forgetting that this 0.808333 is the same 0.0833 that we have there. Multiply it by the 4, which just lets us know how big our sample is. And that gives us the variance between samples. Or what I would like to call it, but I'm not, the variance between sample means. Okay. All right. So I'm going to move on now. Looking at the degrees of freedom, how do we calculate the degrees of freedom? I guess the one thing that we need to write on here is let people know what K is. Thinking about Ice Cube right now, cross them out and put a K, right? K is the number of categories. Right? So if you got 4 categories, that would be 4 minus 3 would be the numerator degrees of freedom. If we're doing the denominator, the equation for getting the degrees of freedom is k times n minus 1, right? N is referring to the sample size of each of them, and you multiply them by the number of groups you have. So that's how we can find the numerator and denominator degrees of freedom. And then that will allow us to go in and pick the, and that will allow us to know exactly where we want to go on this chart. Because we'll have the numerator degrees of freedom, right? We'll have the numerator degrees of freedom from the one equation, and then we'll have the denominator degrees of freedom from the second equation. And then we'll be able to find, okay, what's our critical value that we need to exceed to say, there's no way these results are the same. All right, now, you know what? The end of class crept up on me. I had no idea it was the end of class. One thing I'm going to ask everybody to do is this, and you probably can do it in the last couple of minutes.